Math 3 Lesson Summary Video. Diggin. This lesson is a develop understanding task, which is meant to introduce you to a concept, but not necessarily finalize rules or strategies. The purpose of this task is to introduce radians as measures of angles in concentric circles, and how to quickly find the radian measure using fractions. It will also review the concept of special right triangles. After looking at the model of the archaeological dig, Veronica says they need to have more stakes if they intend to be specific with the location of the artifacts. Since most archaeological sites use a grid to mark off sections, Veronica suggests evenly spacing 12 stakes around each circle using the coordinate grid to label the location of these stakes. The central tower is located at the origin, and the first of each set of 12 stakes for the inner and outer circles is placed at the point 12, 0 and 18, 0. That made the most sense because we know the radius is 12 and we know the radius is 18, so that makes it a nice even point to figure out. Now our job is to figure out how we are going to space out 12 equal stakes all the way around. So that means we're cutting our circle into 12 equal pieces. So 12 at least splits in half easily, so that means we should have 6 pieces on the top and 6 pieces on the bottom, and it'll even split into fourths evenly, so we want to have 3 pieces in each quadrant of our circle. So I can go around and get some stakes. If this is stake number 1, they've got it labeled as stake number 1, then I can figure out I do have a stake here and here. I have a stake here and here. I have a stake here and here. And that at least gets us cut into the 4 quadrants. And each quadrant now needs to be split into 3 equal pieces. So we kind of want to slice our pie into 3 equal pieces. So somewhere around here and here is going to give us 3 equal pieces in that quadrant. So this would be stake 2, this would be stake 3, that means this is stake 4, and now we can try and divide this one into 3 equal slices, and we'll get our stake 5, our stake 6, and our stake 7. So we're going to have to finish this for the whole circle, but we'll start with the top. Stake 1, we already have its coordinates and its lengths. So let's work on the next easiest one to me would be stake 4 because it's going straight up and down. It also is just the radius. So its point is going to be 0, 12 or 0, 18 because it's just going the radius straight up. So its x coordinates don't go left or right any. So we have 0, 12. And 0, 18. We want to know its distance from 12, 0 along the circular path, and we know that's the arc length. So as we're doing the arc length for that little section, we want to find the circumference of the whole circle, and then we can figure out what 1/4 of that would be. So that seems fairly easy. So circumference of a circle is diameter times pi. So since this one has a radius of 12, its diameter is 24, and 24 times pi is 24 pi. And 1/4 of that, if we do 1/4 of 24 pi, that's just going to be 6 pi. Cool. And if we want to do the ratio of the arc length to the radius, so our arc length is 6 pi and the radius is 12. So if we do 6 pi over 12, that's going to reduce to be pi divided by 2. And if you recall from the circles unit, the ratio of the arc length to the radius is what we called the radian measure. So we're looking for the radian measure there. And so we found it to be pi over 2. Now, We also learned during the circle unit that if your circles have bigger radii, the ratio still turns out to be the same. Let's see, the circumference of the 18 radius circle would be a diameter of 36, so 36 pi. And 1/4 of 36 pi would be 9 pi. And if we do 9 pi over the radius, 18, we do get pi over 2. So now we know that this stake has a radian measure of pi over 2. We know its coordinates, and now we can work on some of the other ones. Thinking back to our Ferris wheel problems, we know to find the coordinates of the point, we are going to have to use a reference triangle. So we can draw that the vertical line down to the horizontal axis. We know the x-coordinate will be this side of the triangle, and the y-coordinate is going to be this side of the triangle. We know that our radius is still going to be 12 for the smaller circle and 18 for the larger circle. And we can find the needed coordinates for our stake. So to do this is probably going to require a little bit of the trigonometry that we talked about. If you recall from earlier lessons, in the lessons 1 through 5, we figured out that the x-coordinate is always equal to the radius times the cosine of the angle. And we know that the y-coordinate is equal to the radius times the sine of the angle. So to make this go a little quicker, it would be helpful to know what is that angle for each of these reference triangles. So if we think about our whole circle, we know that the whole circle is 360, but we're dividing it into 12 equal pieces. And if we do 360 divided by 12, we actually get 30 degrees. So each of the pi pieces has an inner angle here of 30 degrees. So if I'm going to find what my x-coordinate is for the first one, I can just do the radius times the cosine of 30 and the radius times the sine of 30. What's interesting about that, or hard about that, is that I'm going to get decimal answers. And we've already started writing exact answers. Keeping things in pi just is so much easier. There's no decimals. We can just keep it nice and clean and not have to round anything and keep everything exact. And we would really love to be able to do that with our other points as well. Veronica really said she wanted it to be more specific. That's why we're putting more stakes. So how might I find the lengths of these different sides and actually get an exact answer and not a decimal answer? And that's where it's helpful for us to go back and remember our special right triangles. If you recall from Math 2, we learned that certain triangles have ratios that are worth remembering. And we learned the 30, 60, 90 triangle. We also learned the 45, 45, 90 triangle, but these were, the angles in this circle were 30 degrees. And so if we go back to our picture before, you remember that when we dropped that vertical line down, this angle was 30 degrees, which meant that it was a 30, 60, 90 right triangle. And so we had a pattern that we memorized last year to help us to find the sides of a 30, 60, 90 triangle. So in the small circle, we knew that the radius was 12. And our pattern tells us that that is equal to 2a. A is the shorter side of the triangle. It's the side directly opposite the 30-degree angle. So if the hypotenuse is 12, that would mean that A would have to be 6. And then in order to find that longer side, the longer leg of the right triangle, we always have to take that shorter side and just multiply it by the square root of 3. So that would mean that this side is 6 square roots of 3. So we could use this special right triangle rule that we learned back in Math 2 to help us to find our coordinates for our points as we go around, because all of these reference triangles are going to turn out to be 30, 60, 90 triangles. The second one, it would have a 60-degree angle at the center, so its reference triangle would look something like this. And again, we know that the radius is 12, therefore the smaller side must be 6, and the longer side must be 6 square roots of 3. So if we go back to our circle and we think about that first stake after we got started, we have our two right triangles here, and we know that this has a radius of 12, so the smaller side must be 6, and the longer side must be 6 square roots of 3. So for stake number 2 on the 12-foot circle, it looks like our x-coordinate will be 6 square roots of 3, and our y-coordinate is going to be 6. And for that second, or the third stake, stake number 3, that's that 60-degree angle. Again, if our radius is 12, the shorter side is 6, and the longer side is 6 square roots of 3. So its point is going to be 6 square roots of 3. We can do the same thing for the 18-foot circle. So if the radius is 18, the smaller side is 9, and the longer side is 9 square roots of 3. So we're going to get 9 square roots of 3, 9, and 9 square roots of 3. You may also recall that when we were doing our Ferris wheel, we learned very quickly, and used it to our advantage, that symmetry in a circle is very useful. So when we keep continuing around 30, 60, 90, 120, 150, 180, this reference triangle still has a 30-degree angle. And this reference triangle still has a 30-degree angle. This reference triangle still has a 60-degree angle. These points are going to coincide with these points. The only thing that's changing is our sign. Don't forget, points in the first quadrant are positive, positive. Points in the second quadrant are negative, positive. Points in the third quadrant are negative, negative. And points in the fourth quadrant are positive, negative. So we can use the fact that stake 2 is 6 square roots of 3, 6, to get that 4, 5, 6. Stake number 6 is going to have to be negative 6 square roots of 3, positive 6. If we're looking at stake number 5, it coincides with this one. So it's going to be the same thing, except it's going to be negative 6, positive 6 square roots of 3. And so we can use that symmetry to our advantage as well. Same thing over here with our 18-foot circle. They're going to have to coincide. So negative 9 square roots of 3, 9, and negative 9 square roots of 3. So they'll be the same point. We're just going to change the sign. We are still going to be able to find, we already knew that the circumference of the smaller circle was 24 pi, and the circumference of the larger circle was 36 pi. So we can still figure out our proportions because we know this one was 1/12. So it's just a 1/12 of this particular circle. So that means that it has a distance of 2 pi. And without overthinking it, if this length is 2 pi, that means all of the little lengths are 2 pi. So we don't really have to sit and do a lot of math to try and figure out what the arc length is going to be for the next one, because we're just counting by 2 pi lengths. So that means stake number 3 must have a distance of 4 pi. And stake number 4 would have to be 6 pi. And stake number 5 would have to be 8 pi. And stake number 6 would have to be 10 pi. We know that the radius for this one is 12, so 2 pi divided by 12 would be 1/6 pi. 4 over 12 would be 1/3 pi. 6 over 12 would be half of pi. 8 over 12 is going to be 2/3 pi. And 10 over 12 is going to be 5/6 of pi. And so we can do those ratios to figure out our radian measure. But if you think about the circle as a whole, we've already discussed that each of these little pieces is 1/12 of the circle. And if you think back to the circle unit and what we learned about radians, we know that the whole circle is 2 pi radians. Half of the circle is just pi radians. And so if we actually think about our circle and just think about fractions, we can actually figure out that radian measure without having to do any of the circumference or arc length measurements. If we just acknowledge the fact that half of the circle is pi radians, and we just divided that half of the circle into 1, 2, 3, 4, 5, 6 equal pieces, then this would be 1/6. This would be 2/6. This would be 3/6, 4/6, 5/6, and 6/6. We're just counting how many sixths there are. Now you reduce those fractions. 2/6 reduces to 1/3, 3/6, 1/2, so forth and so on. But finding these measures, I don't have to memorize anything. If I'm going to divide this into 12 equal pieces, the radian measure is just going to be 1/6 of pi for each one. So I can continue counting. 1/6, 2/6, 3/6, 4/6, 5/6, 6/6. That would make this one 7/6. This one would be 8/6, 9/6, 10/6, 11/6, and back to 12/6. Now, some of those fractions do need to be reduced. 8/6, it actually reduces to 4/3. So you would want to make sure you reduce that fraction. 9/6 is going to reduce to 3/2. 10/6 is going to reduce to 5/3. 11/6 doesn't reduce. And 12/6 reduces to 2 pi, which we knew already. We know the whole circle is 2 pi radians. So we can figure out these radian measures to go along with the angle measures. We can also figure out the angle measures pretty quickly. Not because we have to sit here and do our conversions to convert 5 pi over 6 to degrees. We learned how to do that in the circle unit. But if we know that the circle is 360 degrees, and we figured out that 1/12 of that was 30 degrees, we just have to count by 30s. So 30, 60, 90, 120, 150, 180, 210, 240, 270, 310, 300, 330, and 360. So I don't have to do a conversion. Now I could just count to figure out, oh, well, 4/3 pi is 240 degrees. And so you really want to think of the circle and its pieces as fractions. Fractions really are our friend, and we want to use them to our advantage.